Yeah. So, hello everyone today. Welcome to our webinar. I hope you can see my screen. Please can someone type in the questions box if you do see it, yes or no, and if the question box works, that would be really helpful. Thanks. My talk today will be about the real space and how we make 11 billion compounds purchasable. And what is the chemical space? So there is a publication which is always named, which from Bohacek et al., quite old actually, from 1996, and they say the chemical space is about 10 to the power of 63. And how far have we come so far? Yeah, everyone purchases compounds from e-molecules at the moment. That's about 7 million you can buy in there in the extended set. And there are other approaches like the real database or the zinc database, which have about 750 million virtual compounds in there. And all those methods have something in common. They enumerate the molecules. That makes a lot of data and creates quite long searching times as well. And there's just a way where you cannot handle more compounds than about billions. And we have a quite different approach in here. We do in silico synthesis. Means like we teach the computer chemical reactions and the reagents that can be used in those reactions. Equally, this is combined with a fast searching algorithm and makes huge spaces accessible. So those libraries or those spaces that we do are not enumerated, means like they're not every compound individually written down in the computer. It's so that they don't need to be touched individually, because that's kind of the drawback of those enumerated libraries. They require just very huge disk sizes. So there's a quite famous paper from the group in Bern from Professor Jean-Louis Raymond. They make the GDB databases, and they have a database of about 160 billion molecules, and just zipped smarts terms in there have about 0.4 terabytes already. So imagine how this data explores when you unzip them and create 3D coordinates and that and that and that, so you can hardly handle those methods. And there are quite good methods to search in those conventional databases, like in 2D, the Arthur algorithm from NextMove, or when you want to do the 3D, it's FastRock from OpenEye. There's currently quite good methods to go that. But even if you ask Roger Sales, so the owner of NextMove, what do you do when you come over the billion? He says, I have to give up at the moment. He doesn't know how to handle this. So how is our approach different from this? We, as I said, teach the computer chemistry, like, for example, here the Suzuki reaction. And in the next step, we search for all the reagents that match. And we remove the atoms that undergo the reaction and add those linker atoms, depicted here by the Lego bricks. And on the product side, we really do not have a real molecule, but we have those fragments and the matrix that says which linker is compatible to which one. So in this case, a yellow Lego brick matches on a green Lego brick. If we add more reagents, you can see that the product side would explode, but we just kind of keep the left side. We have only those fragments here with the linkers on them and the big matrix on how to link them. I just muted the rest of you. I'm sorry. Many of you are logged in as organizers, and there's a little bit of feedback loop here for me. Okay, so how do we achieve the goal here? As you saw before, when we have those reactions and the linkers, we can add many, many more reactions, and they will have the same linkers again. For example, here with the boronic acid, you use this in so many coupling reactions, or a carbon with a leaving group, they will occur again. And then you have those linkers again. And in the chemistry space, the pre-processing here, you have lots of little bits of fragments with those linkers on there. And so far we have created different spaces of different sizes. So Boehringer Ingelheim have been early adopters of this. They built the first spaces already in 2010-11, and their space, the BI claim, is about 10 to the power of 17. The biggest space we've built so far is together with Merck. It's 10 to the power of 20 big. There is a public space, which is the knowledge space. You can download this from our website and just search it. This is about 10 to the power of 15. And all these projects were happening but didn't get too much attention until we teamed up with Enamine and created the real space, which is 10 to the power of 10, so 11 billion molecules in there at the moment. And they are purchasable, and that's what people are interested in the moment in. And this space is purchasable because there's quite good control over the chemistry in there. And I don't want to explain this to you myself. I will leave this to Yurii, because he's the expert on what happened in there. And Yurii, I would like you to present the next slides, please, if you don't mind.
Yeah, thank you, Franca. Can you hear me?
Yeah.
Yeah, okay, good. So Enamine universe is rather big, and most of it is actually based on the parallel chemistry. So the chemistry of pretty much accessible reactions and transformations that can be done not in like in one flask, like conventional method, and we used to do when we are in the lab, but done in parallel in vials or plates. And for Enamine now, there are more than 200 parallel chemistry reaction procedures that can use over 150,000 building blocks. And those are really new building blocks, over 2,000 of which actually delivered monthly. If you employ that many building blocks and that many reactions, you can get to the trillions of molecules. Next.
Oops.
Oh yeah. But in reality, you don't know whether you can get molecules from those trillions, but you can definitely get the molecules from the real space. And the real space is the space of the molecules that are based on validated chemistry and qualified reagents. This space, the molecules from this space are accessible within 3 weeks with really high success rate. And now, as Franca mentioned, we have having billions of those molecules. Next. So when I say validated chemistry, I mean that the procedures to build this space are really validated in few thousand experiments, and only those procedures that result molecules with a high success rate they included in the enumeration. And for the procedures that are presented, let's say less successful results, we do the additional evaluation, and if this procedure is not good for giving us the accepted success rate, we're not included in the real space. Next. The same we do for the building blocks. We do validate each building block that is received from the warehouse, at least in several reactions. And if we see that the building block is okay and it can be used in our conditions, we included it in the enumeration. For the building blocks with the low score that present less successful experiments, we don't do the enumeration before we optimize the conditions. If we can do optimization, we do not include the building block in the enumeration. So this means we use validated chemistry and qualified reagents to build the space. Next. And the current release of this 11 billion space is based on 121 high score reactions that are 1 to 3 steps with the inclusion of 2 to 3 reagents. And it's pretty diverse because we included over 75,000 qualified in-stock building blocks. Next.
Yeah. So from here it's me again then. And I always like to show this on a linear scale at least once so people can imagine better, because 11 billion is such a crazy number that's just so much more than everything else. So if you have here, for example, the 6 million from the molecules plus, or I don't know, here the zinc database, which is really well known, and the real database that many of you use for years. You have then here the last release of the real space, and now I have to zoom out actually a little bit, that you can see now the 11 billion, that's this on a regular scale, on a linear scale, so not logarithmic. And if you see that our first real space release in 2018 was on the 650 million, so pretty close to what's in the real database right now. And then the version from May last year was already 4 billion. Now we're on 11 billion. You see how fast this grows. And yeah, for comparison, all the enumerated libraries, again, stop here at about the billion border because they can just not really nicely handle bigger data volumes in terms of what RAM they will need and what storage they need in the computer. The question is now, how do we search in that space? I showed you how we process the reactions, add the linkers, and have those fragment spaces here. But when I come with a query, how do I get my results back here and kind of according reaction information, how to make those compounds? We have a quite unique navigation approach for this. The algorithm behind it is called FeatureTrees. And FeatureTrees basically takes your query molecule that you submit to the space and translates it into such a tree of Pharmacophore nodes. And each of those nodes contains exact information about the Pharmacophore which is behind it. So, for example, the piperazine ring here has a volume of 44 cubic angstrom, has a ring count of 1, has some donor acceptor features, but no aromatic or amidic features, and a bit of hydrophobic feature. And so those are the bits that are searched in the space. And when you then have this tree of your query, the algorithm will come back with a second tree of your hit molecules, which is then retranslated into a molecule. So if you go into the real space with a molecule like this here, you will come back with a hit like this. And actually, lots of people always look at this and say, on the first glimpse, those molecules are not really similar to each other. And I deliberately always take this example because both molecules are known active PDE5 inhibitors. So the algorithm can The algorithm is able to not only find close analogs, but do scaffold hops as well. And what's really, really nice is the engine gives you back those mapping pictures as well. So you can basically understand why the computer found those two molecules similar. So if you see those two cycles are there again, and actually the amide is again there, but outside of the ring, and then you have the aromatic core, the sulfonamide, and so on. So you can really understand why there is a similarity seen. And as those are aligned trees, you can of course pretty easily go over and do a 3D alignment and work ligand-based with this approach if you want. And those scaffold hops are quite good approved. So FeatureTrees is a very old algorithm, actually was invented in the 1990s, and people did the first evaluation studies in the late 90s. And so you see here people search for D4 antagonists in the WDI back then, and while screening the first 2% of the database, they found lots of actives. So all the dark lines in here stand for one active D4 agonist. So you see within the 2 first person of the database you've searched, you come back with active molecules, and whilst you still here see the similarity between the first few on rank 22, so we're still up here, you can already see molecules which are distinct away from your query, and you might easily miss them if you do just standard substructure search or go for Morgan fingerprints and Tanimoto similarity and all those approved methods. So FTrees is basically a little bit more fuzzy and helps you to go over good scaffold hops. Okay, but I told you so far the space is not enumerated, so how does it really work? The space itself with the linker atoms on there consists of the fragments with the linkers, and those fragments are basically little feature tree bits. So when you come here with your query, the search algorithm will go through those FTrees bits with the linkers and reassemble the molecules according to your query. So you don't have to stir the full molecules. They will be reassembled whilst you search for the molecule you're interested in. And what's quite new in there is you can define as well favorite features, so you can rank importance of which feature tree node is most important for you, and you can click on those parts of the molecule and say, but this one shall be very similar, or this one actually I want to have still pharmacophoric similar, but with a lower F-tree similarity, so a little bit distinct from your starting point. So a good example for using those favorite features is when you look for certain motifs, like a hinge binder, for example. So I've looked for this molecule in the space, and without setting any favorites, and did a docking study afterwards. I could only about dock half of the molecules, and there was not the proper hinge binding motif retained anymore. So many of them bound in a quite weird way. And then I introduced minimum similarity on either the nitrogen of the thiazole and of the amine group here. And with those favorite definitions, I could dock a way higher number, and lots of them showed quite standard hinge binding motifs, and I retained many amino thiazoles as well. So how can you get there is the question. How can you access all the things? There is a NIME node which allows you to search in real space or other spaces. There is a pipeline pilot node to search in the space, and for the real space itself, we have the real space navigator. That's a quite easy to use interface. You have a field here where you can paste your query as in SMILED or a SD file, and up there is a little slider saying more similar or more surprise. Means like, do you want to stay very, very close to your query molecule, or do you want to be further away? So one use case for being very similar would be if you've done a primary screen on any target and screened one of the standard Enamine libraries, for example, and you want to get an SAR around your molecule, you would search for more similar ones. If you're a little bit later in a project and have some molecules that you know are good binders but have a PK problem or are patented or whatever your problem is with those molecules, you would put the slider further down to the more surprise side to come back with molecules which show better scaffold hops but still pharmacophore similar properties. And then you would get the results list after a few minutes and save those. The big brother, so to say, of the real space navigator is a tool from us called Infinity. This contains as well the favorite feature, as I've showed you before, and this tool is able as well to search in several spaces at the same time. So you see in here, for example, I've searched in the knowledge space and the real space at the same time, and you get here information as well, which source this came from, and you see those matching pictures in this tool as well. So what's quite important for many people is that all those tools run locally. So you can unplug your computer from the internet and it will still search in a billion molecules. It's all safely behind your firewall. Those are little apps that will just run completely local on you. And this is possible because it's only those fragments. Yeah? So you really have nothing more to store than those fragments with the linkers and the compatibility matrix. And this can be easily kept in an 8 GB RAM laptop. Yeah. Okay, so it works. I told you before, many companies use this for a long time, but as it is, there's hardly anything published in here. But we recently scanned for something I'm allowed to talk about. We've looked for an SAR by spacer approach around BRD4 inhibitors by taking some active molecules, searching them in the real space, docking and scoring the molecules, inspecting them, selecting some, and really I've ordered them at the Enamine people, and I can say that from the 32 molecules I've ordered, 31 came back. So Enamine always says they deliver about 80% of the compounds. From all I know, talking to customers, I can say that the number is a little bit higher actually. I would guess it's around 90. And yeah, there are actives under them. Unfortunately, the manuscript's not ready yet, so I'm not allowed to talk too many about it. Just to sum up a little bit, so there's a worldwide unique technology for creating and searching those huge spaces. And just to give you about a number, searching the real space on my computer takes about 2 minutes. So that's quite a lot if you think about that this is 11 billion compounds. And the software to create the space is called Colibri, which can easily help you to create your own chemical spaces. If you think that you want to go away from the patented areas or kind of fully use your own potential of IP that you have in-house. Yeah, I mentioned the example of Merkur in Germany, which built the massive space, which contains their chemistry and their building blocks. So they really created their own world of chemistry, or Böhringer, as I said before. And yeah, most of you are here today because Enamine offers the world's largest compound-on-demand collection this way. As I said, more than 80% within less than 3 weeks. And yeah, Yurii is here with me, so he's the contact if you are interested in purchasing compounds. And with that, I'd like to thank you for your attention, and I'm happy to take questions.